Okay, so part A asks us about the speed of this wave that's travelling along a guitar string. So whenever you have questions about the speed of a wave, the key relationship is that. Whether it's a light wave or any other kind of wave, that's the key relationship, where c is the speed of the wave, f is the frequency, lambda is the wavelength. So we've got the frequency in the question, so we've got to find the wavelength, and that you get from the diagram. So one wavelength, remember, is the distance it takes for the wave to get to the next point that's in phase with the point where you start. So in other words, the next point that's in phase with that one is here, because it's at the same displacement, which in this case is 0, and it's travelling in the same direction. So one wavelength corresponds to that, and then you can see that it then repeats. So if that whole distance is 0.66 meters, that's obviously 1.5 wavelengths, so we get 1.5 lambda is equal to 0.66 meters, and so lambda is equal to 0.66 divided by 1.5, which is 0.44 meters. And then we just plug the numbers into the expression. So that's equal to 330 times 0.44, which works out as 145 meters per second. So for part B, when you get a question that's asking you to relate the tension in a string to the frequency, then hopefully your first thought is that you're going to use that relationship, which is on your data sheet. You got to be careful though, because remember that, as it says on the sheet, is for the first harmonic, and this is not the first harmonic. So first of all, we need to figure out what the frequency of the first harmonic would be, given that that's the frequency for this one. So if you remember how these harmonics work, if this is the end of the string, the first harmonic looks like that. So there are no nodes in between the two fixed points at the end. So that would be the first harmonic. Second harmonic looks like this. So with the one node in the middle. And the third harmonic looks like this. And you can see that that's what we've got here. Okay, this corresponds to the third harmonic. And of course the point is that means that the wavelength is different. So that corresponds to half a wavelength for the first harmonic, whereas it's now a whole wavelength, and now it's 1.5 wavelengths, as we've already discussed in part A. So that means that lambda for the third harmonic is only 1/3 of lambda for the first harmonic. Okay, and you can see that from the diagram, because that's 1/2 a wavelength and that's 3/2 of a wavelength, but it's the same distance. Now the relationship, remember, is that c is equal to f lambda. That's the relationship between the frequency and the wavelength. And c, which is the speed of the wave, which you can think of as the speed of the individual waves, which remember travel in opposite directions down the wave to generate the standing wave. That's a fixed number. That's just a property of the string. It's not a property of what particular wave it is that's travelling on that string. So what that means is that because lambda for the first harmonic is 3 times f for the third harmonic, which is 330 Hertz, that means that f must be 1/3 of the frequency of the third harmonic, because when you multiply them together they've got to give the same number. So because the wavelength is going to be 3 times longer for this first harmonic. That means the frequency is only going to be 1/3 of that value. So that was the frequency for the third harmonic. So that means that the frequency for the first harmonic is going to be 110 Hertz rather than 330. So that's going to be important when we come to putting the numbers into there. Now the next number we need for putting into here is mu. So mu, remember, is m over L. So it's the mass of the string divided by the length of the string. So we've got the numbers for that in the question. So it told us that the mass was 3.1 grams, but remember that's got to be in kilograms. So we're using the SI unit, so it's 3.1 times 10 to the minus 3 kilograms divided by 0.91 meters. And so we can plug those numbers in and we get 3.407 times 10 to the minus 3 kilograms per meter. Okay, so we're going to need that number as well when we come to plug in the numbers into here. So let's then rearrange that expression. So first of all we can move the 2L over to the other side. So we get 2L times F is equal to root T over mu. We're trying to solve for T, remember, so we need to get rid of the square root, so we're going to square both sides. So we get 2LF squared is equal to T over mu. And then we can move the mu over to that side and get 2LF squared mu is equal to T. So that is the relationship that we need. So now we can plug the numbers in. We get T is equal to 2 times, now L, you've got to be very, very careful about L, because it's not the total length of the string, because remember it said the total length of the string was 0.91 meters, but some of the string is kind of hanging off the end here. So part of that 0.91 meters is not part of the stretched length, and therefore the wave is not covering the full 0.91 meters. We were told this was 0.66 meters. That's the length in which the wave is being formed in the stretched length. So you've got to be careful to make sure that you put the right value for L in there. So it's 2 times 0.66 is the length of the stretched bit where the wave is, times 110 Hertz, we decided was the frequency for the first harmonic, all of that squared, times mu, which is 3.407 times 10 to the minus 3. And if you work all of that out, you get 71.8, and that will be in newtons because it's a tension. And so that's your answer.